So, welcome back to the next episode of our series on architecture of business applications. Awesome stuff shall be discussed, and I hope some of it will scare you. Well, it scares me, so I'm just extrapolating. So what are we doing in this episode? In this episode, we're going to look at the typical architecture related tools that we as architects use to try to achieve certain results. Okay, what are the tools at our disposal? What are the things that we can do to that college student stack in order to deliver on all sorts of challenging NFRs? Okay, so the first thing that I'd like to do is look at a relatively larger applications stack, as in what are the pieces that are in place. Some of them are hardware, some of them are software, which comprise like a non-trivial running application. Okay, so let's look at the layers. So we're going to look at the layers from the outside in, as in the outermost is of course the internet, from where the front end programs, mobile apps, etc. hit the stack. So the internet. From the internet, the first thing that you hit in a relatively larger, I'm talking about, large enterprise applications today. So the first thing that you will hit will be load balancers, because you will want to make sure that your load is distributed across multiple machines, etc., etc. And if one goes down, things will fail over to the other, etc. So the first pair of boxes are the load balancers. These arrows indicate accesses coming from the internet. Now, extending it a little further, each load balancer will hit API gateways. Okay, so we are only showing one of the load balancers here, drilling down further. The other load balancer will do the same, but now each API gateway will then hit application servers. Modern non-monolithic applications need API gateways. It's a little difficult to set things up without API gateways. So load balancer, API gateway, application servers. Now each of these green, blue colored boxes that you see is supposed to represent a physical bare metal server or a virtual machine or a container. We are not getting into that sort of specification, but these are application servers. They are communicating, these application servers, the code in the application servers is communicating east to west in a parallel, in a horizontal line, using an enterprise services bus or a message bus. Then finally comes the databases, the data store. Now, if you look at what we are trying to show in the diagram, we have tried to picture a slightly non-trivial large application. So we are depicting here a situation where we have split the data into two parts: the data which is fast changing and the data which is not changing much. Typically master tables don't change fast. Various report and MIS data or summary data don't change much, but transaction data changes very fast. So we are talking about two databases so that we can optimize them for two different types of response and performance and so on. So we are saying that we have two databases, one for slow changing data, and one for fast changing data, transaction data. Okay. And then again, this is a typical scenario in the real world where we have large enterprise applications. We can have multiple mirrors of that data. So each database is actually not a single database, as in not a single instance of the database server. There are, say, 5 databases running on with 5 different copies of the database server, and the data is being mirrored across them. This mirroring can be done through master slave replication, which is quite commonly available in most databases, or other means. Okay, so we have all these moving parts which together make up the architecture of we have not even gotten into the software related components of the architecture yet, but at a box level these are the components of the architecture which make up a large enterprise application today. This was just an intro, sort of to give you a flavor of the pieces we have to play with. Now let's look at the tools and patterns. What do we do? What are the tools we play with? And what are the typical patterns of responses that an architect uses to address the NFR constraints? So if you require huge throughput, the architect's first solution is to get multiple boxes parallel to each other, horizontal scalability, scale out as it is called, by adding more instances of the same processing units. Okay, there are limitations, there are issues there which we'll talk about later, but this is the first reaction. The second tool that you play with is use RAM instead of a relational database. Keep data in RAM if possible. So when you have huge throughput constraints, don't directly write each and everything that you need to directly into a relational database. The third kind of scenario is where you have latency expectations, where you need to respond very, very fast, or you need to complete each operation in a very small number of milliseconds. What do you do there? Okay. The first tool at your disposal is once again RAM. For read queries, keep the data in RAM, use the RAM as a cache. For database writes, there is a very powerful weapon which needs to be used carefully if you're doing it at application level, or can require a completely separate class of databases if you're doing it at the database level, and that's sharding the data. Sharding means splitting the data set into disjoint subsets. So if I have 1 million records, I may shard them into two shards, where one shard only has 500,000 and the other shard has the other 500,000. So in effect, there will be no data store there will be no database which will have the entire 1 million records in one place. So that is sharding. For peakiness of load, when loads are very peaky, which means you have low load most of the time, but extremely high load for short bursts, what do you do at that time? On the cloud, use auto scaling. One of the earliest appeals of these public clouds was that they gave you auto scaling facilities. You could spin up and spin down instances on demand. One step further, which actually makes auto scaling automatic, where you don't have to do any scaling, is you use serverless blocks. Serverless blocks could be of various kinds, but go serverless. In hard data centers, what I mean by hard data centers is a data center which you physically own and administer, where you have bare metal hardware to manage. In such hard data centers, you can think about warm standby machines which are running but are not actually executing your load. Maybe they are powered down or semi-powered down or working in low power mode, which you can spin up if there is very heavy load. Or you could have a pool of general resources from which you can automatically apportion some resources to handle the peak. I'm not getting into details here. This is a fairly high level overview of the things that one can do. There is one kind of peakiness where you might have different types of services or subsystems which don't all peak at the same time. So maybe during annual closing of your books of accounts, your financial accounting system exhibits peak load. During maybe retail sales time, your Diwali dhamaka or your Black Friday, your retail sales system exhibits peak load, etc., etc. So if the peakiness is segmented, it is not all across the entire application, then you might be able to have a pool of containers which can then be spun up or spun down based on automatic orchestration. So containers are very useful in that kind of a situation. You spin up only a minimum number, keep them working, ticking away happily. When it's required, more instances of the containers can be spun up. What does an architect do when he has to handle very large data sizes? One of the things we find which is often not done is archiving of old data. I am looking at this e-commerce site run by one of these organizations, and they're using Magento, and they have 5 years worth of orders in the order table. Why do they need 5 years of orders? Every line item of every order for the last 5 years are sitting in that order table. So queries will become slow, data set size increases, etc., etc. Archive old data to hierarchical storage, and of course the cloud gives an absolutely awesome, unprecedented level of options for archival of data if you need to do long-term archival. The second option is take a different approach, do data lakes. Don't get into relational databases, keep raw data, use tools like Athena or other tools which will be able to deliver queries on the raw data formats themselves. Next come situations where you need to do very fast searches through a large database. This is another situation where we find it's good to step out of the classic mindset of the relational database with its ACID properties and SQL statements. You can choose to move data or replicate data into a non-SQL database. Elasticsearch is very powerful, very suitable for very interesting queries, sometimes more interesting than what you can do on relational databases, and they are faster. Elasticsearch is lighter. So move your fast searches away from your main database and often to a non-SQL database to get the benefits of speed and also reducing the load on your transaction databases. So these are some of the patterns you can play with. Other patterns. When you have requirement for high availability, the first reaction and the good reaction is to have redundant clusters of everything. So your application servers are replicated, your data is replicated, data stores are replicating, you have primary, backup, etc., etc. All of that this is the classic solution. We will get into the details of replication and redundancy sometime down the road in some of the other episodes. What about access patterns, where you need to enforce certain access patterns and you need to be very careful about disclosure of confidential data, etc., etc. There, the classic solution is to define circles, like layers of an onion. So the most confidential data is in the innermost circle. The circle just outside that will have a little less confidential data, and so on and so forth. So data itself is not stored all in the same place. Keep data in different circles depending upon security and confidentiality constraints. So there are various security professionals will tell you about defense in depth and how you can apply that, especially when you have layers and layers of access or controls between the outermost layer and your innermost data. One of the things we find very useful from the security point of view is to not keep all your data in one big relational database. If you do keep all your data there, then any intruder who somehow gets SQL level access to that database is able to pull out all the data that he wants, even the data that he doesn't want. He can do like select star on all sorts of tables and pull out data. He may just do a query to find out what tables exist and pull out data from those tables and so on. So it's a little difficult to implement defense in depth if all your data is in one big, handy, very powerful, very flexible relational database. So split the data into different layers, move them to different data stores. Then the issue of compliance. Where you have data residency laws, you have no option but to break up the data into multiple data stores. So one data store in each country. Of course, these public cloud fellows make it super easy because they give you multiple availability zones for their services in multiple countries. So you just click from a menu and your data goes somewhere else. So you can do all that, but of course, very often application code also needs to change, particularly when you're doing queries on the aggregates. The second constraint is forget me laws about data privacy, PDPR. So if a customer has the right to demand that you have to forget the customer in your records, then you should index your data appropriately by customer ID so that you can, trawl through all your data stores of all kinds of data based on just the customer ID and then remove the data records which are pertinent to that customer. And you look at more sophisticated logging for compliance, because whenever there is compliance, it's a gray area how much you have to do to demonstrate that you are complying. It's easy to say, I have a compliance requirement. It's a little more difficult when the regulatory authority says, demonstrate to us that you indeed are complying. How do you prove it? So additional levels of logging for traceability are very useful here. So these can impact architecture, because sometimes you may need to have separate data stores, separate log repositories just to deliver on this compliance. Now we'll look at a common problem, which is one of the, I think, most popular challenges that architects face, which is horizontal scalability. How do you scale? Everybody wants to scale, everybody wants to talk about how they can scale and how they can handle huge volumes and so on. So what are the challenges here? One of the most basic steps is to separate code from data so that code can be replicated. See, the horizontal scalability involves replication. You replicate various units, whether it's data units or processing units. If you wish to replicate, if you wish to do this spreading horizontally bit, then your data cannot be with the code. Otherwise, your code will replicate and the data will also replicate, and where you needed one copy of the data, you will now have 5 redundant copies and there will be no data consistency. So you need to separate code from the data. This is not as obvious as it sounds, because everybody today will separate out the relational database data from their code. But there are all sorts of other data units which are not relational database data, which are often left behind or are strewn around in a mess. For instance, configuration information. We usually find that architects address scalability challenges by scaling up the application servers. Low-hanging fruit. I understand it's easy to do. It requires less thinking. So go ahead and do it. The problem is that it doesn't solve the performance bottleneck. Very often the transaction database is the bottleneck. Now in that case, you need to do a reality check. Okay, we did one trivial benchmark. One slightly high-end desktop with an i7 CPU, 26 cores, 32 gig of RAM, which is not a huge amount of RAM. We were able to push in 40,000 insert transactions per second into Postgres. 40,000 per second exceeds a lot of the transaction requirements of a lot of large applications which we've developed. So it's a very large number. So the first thing to do is the transaction database a bottleneck, is what you need to check. It often is a bottleneck, and it is not necessarily because hardware is slow. If you throw hardware at the problem, it may not speed up, because look at the incredible performance fairly ordinary hardware is giving for transactions. So why are they slow? They are slow often because the transaction database is not just handling transactions, it's also handling queries, it's also handling all sorts of report generation, and there may be various other reasons for it. There could be hotspots. I'll give you an example of a hotspot. It's so customary for these business application developers to create a table where they'll have an auto incremented ID. The ID column will be an auto incrementing integer. What this means is, I will insert a record, the database will increment the ID somewhere. It keeps an ID variable somewhere, which it calls a sequence. It increments the sequence and it assigns the new value of that ID to the new record. I insert a second record, another value is automatically created and assigned. Now, whenever there are 20 different or 50 different streams of transactions hitting the database, everybody wants the next sequence, and that sequence becomes a bottleneck. So for higher throughput, you need to shard your data. If one database is not enough, and it is a transaction database, not a reporting or a query database, then you need to shard the database. But first you need to benchmark your hardware. You need to actually see what is the raw performance you get from the hardware that you have and the database which you have. And sharding is not easy. It requires application code change unless you use database software which does the sharding internally inside the database itself. The next and much easier solution to transaction database bottleneck is to do read-only replicas of your database. Most databases allow read-only replicas. So single master, multiple replicas are supported. So all your updates, inserts, updates, deletes will hit the read-write master copy, and the queries will hit the read-only replicas. So when queries move away from the transaction database, the database has more power left to handle the transactions. So this is a very big help in situations where you are hitting database limits. The next thing you can try is caching. Caching immediately increase your scalability. You have to use caching a little carefully. It's not something that you can use blindly, because blind caching generates problems which we are not even getting into. Okay, so you can use caching intelligently. Use asynchronous databases. This is not used enough. This is a category of solution which is not used enough. Document databases, distributed databases often support asynchronous updates and asynchronous replication. What this means is that you can have a multi-master cluster of databases. So the data is actually spread across multiple servers, and you can update the database by connecting to any of the servers. And when you update a record, that record gets replicated across all the nodes asynchronously, not then and there, maybe after a few milliseconds or even a few seconds. So asynchronous databases which synchronize, which sort of replicate and synchronize asynchronously, they will give you a very high degree of scale up very often. They are not used enough, as I was saying. The other thing that you can do is separate out different types of loads, so that the bottleneck is then isolated into one type of load, and then you can throw all your resources at that problem and try to make sure that you have adequate throughput there. For instance, MIS reports and transactions. If you generate MIS reports from the same database as your transactions, then that's a case where one thing is probably loading the other and preventing the other from moving fast. So separate them out. Now we'll look at the horizontal scalability of a database, again at a high level, conceptual level, but to understand a little more graphically how things work. Okay? So we're going to look at the simplest to the relatively more complex data organization or data store organization and architecture. The simplest architecture is that college student architecture, which is one application server and one database, as the diagram shows. One box on top, one database below. The next level is your read-only replicas. So you have one database which is read-write, and you have multiple replicas of that which are read-only, so they can handle all your queries. So you immediately start splitting queries to the replicas and doing the updates on the master. And the third one is you split the data, shard it. So the diagram that is being shown here uses 4 databases. Your data set is being split 3 ways. So there are 3 shards. So those are the pink colored databases being shown. The application server is here shown as only one. It could be 1 or 10, but the point is one application server is connecting to all 3 databases for updates, and the data set is split across these 3. Now if you see these curved arrows going from below, all of them are pumping their updates to a 4th database, which is a read-only replica. So that read-only replica is an aggregate of these 3 shards. What this means is that for updates you connect to one of the shards, and push out your update. For queries, you don't have to hit 3 databases to do the queries and then aggregate the data yourself. There is already a 4th database which is holding the aggregate of all the data sets. So you can throw all your queries at that one and get your easy, the software development for developing such queries becomes simple. So this is what I'm referring to here as level 2, sharded read-write data. So these are different levels at which you can get horizontal scalability if your database performance is the bottleneck. So that sort of covers, a quick overview of the tools available for us to play with architecture to address challenging NFRs. Next time we are going to step into the zone of these classic terms. What's a service-oriented architecture? What's a microservice? And so on. So, look forward to seeing you next time. Thank you.